get in the video notes. 1, 2, 3. Okay. So do we kind of see how like what we did? This is exactly what we did last unit. We just did not have a variable last unit. So now we're seeing if there was a variable in there, what numbers could we plug in for that variable, and then what type of result would that give us? Does that make sense? So we're really focusing in on the ratio test. We're focusing in, and then we're saying, I'm just explaining the big picture perspective in case with the video doing the individual examples you missed the big picture perspective, okay? So we're saying if we look specifically in at the ratio test, if we had something to an exponent of n, right? Or in any of these different situations, but if we're looking at that type of problem, what number could have been that base that would have allowed it to converge? So last unit, we didn't have x's in the problems, we just had numbers. When we did the test, it was 3 to the n, it was 5 to the n, it was whatever, it was a specific problem, and then we looked at that specific problem, and we figured, does it converge, does it diverge, whatever. Now we're looking, instead of at specific cases, we're looking at general cases, and we're saying, okay, for this general case, what numbers are you allowed to plug in that would make it converge? Does that make sense? So that's kind of the big picture perspective of what we're doing. It took me a while to figure out that's what we were doing. So I just want to make sure that you guys kind of understand that. And at any point, if you say, Miss Rice, back up, I need to understand the big picture perspective of what we're doing again, because I'm starting to lose it in all the rules. Let me know and I will back up and I can explain that again, okay? Because I think that sometimes it helps for us to connect this lesson back to last unit to realize that it really is what we just did. It's not completely separate. It's not a new idea. Okay. So let's look at page 4, since that's what we're on. All right, so if you look at the top of page 4, that looks familiar, right? Focus. My finger's dirty. I put the Maclaurin series on the whiteboard so that if you didn't start your cheat sheet yet, we can just look over there. Those are the 4 that we're going to be memorizing. So we recognize this. We know if c equals 0, it's called a Maclaurin series. Now, we're saying here, instead of f of x is approximately something, I'm using an equal sign. Why am I able to use an equal sign instead of saying approximately? Because it goes to infinity. So as soon as I say that I take this out to infinity, I'm no longer approximating it. I'm doing it exactly. So if it was a 4th degree polynomial, it's an approximation. If it's a 3rd degree polynomial, it's an approximation. If I do this to infinity, it is no longer an approximation, it is equivalent. Does that make sense? Okay, so we're going to say this is an infinite series. So it will go on forever. And the series is the polynomial. So it's the same idea as when we said that we were using rectangles to find the area under a curve. If we used 5 rectangles, that was an approximation. But as soon as we said infinitely many rectangles, then it was the exact area under the curve, because once you go to infinity, you've got it perfect. Does that make sense? Same idea. Okay. So example 3 says, find the first 4 non-zero terms and the general term. Anytime you see that general term, that means like the nth term. For the Taylor series, not polynomial, series, for f of x equals e to the 5x centered at c equals 2. Okay, so we're going to write, we've done this work before, so we're going to say f of x equals e to the 5x, and it says first 4 non-zero terms, so I just need to do 4 of these, so I'm going to go to the third derivative because this is going to count as the first one. So f of x, f prime of x, f double prime of x, f triple prime of x. Okay, so what is the first derivative? 5 e to the 5x. Okay, what's the second derivative? 25 e to the 5x. Or you could think of it as 5 squared e to the 5x. Either one of those would be fine. Okay, and then what's the next one? 125 e to the 5x. Or you could think of it as 5 to the third e to the 5x. Okay. Does that make sense so far? Okay. And then we have to take all of those terms, and if we're centered at c equals 2, then what should we do? Plug in 2. So we're going to say f of 2 is e to the 10. F prime of 2 is 5e to the 10. F double prime of 2 is 5 squared e to the 10. And I'm going to go ahead and write this as 5 squared instead of 25 because I'm preparing myself to write this as an nth term. And as an nth term, it's a little bit easier to use patterns than it is to use the number expanded out. Okay? And then f triple prime of 2 is 5 to the third e to the 10th. Okay. So I'm going to go ahead and write my terms. So my first term is e to the 10th. And I'm writing this as a series, not a polynomial. So I'm not saying p sub blah, blah, blah of x. I'm not writing that because I'm not writing a polynomial. I'm writing a series. So I'm writing first term plus, second term plus, third term plus, and I'm not saying it equals something. Does that make sense, the difference between what we wrote before versus what we're writing now? Okay. So first term plus, and then how do I write the second term? We've got our coefficient, right? 5e to the 10, and then x minus 2. How do we write our third term? Okay. Yeah, 2 factorial or 2, it doesn't matter, both are the same. Okay. And then what's the fourth term? Okay. And then we're going to say plus dot 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 to show that there's some space. So it said the general term. You're good. You're good. That's a good question. And the nth term would be what? Okay. And then this is the important part. This is an infinite series. And so we'll just says for the series. But since we got to the nth term, we're going to put plus dot dot dot. It continues past that. anytime you have an infinite series, your nth term is not the end. Infinite series are forever. So you have an nth term, you have like a pattern where you can say this is, if you want any term past what I've given you, past the fourth, you have an nth term, but we recognize the dot 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 says it is infinite, so it's going to go past my nth term. This is not the ending term, this is just the pattern. So we say, oh, it keeps going, and that's what the plus dot 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 gives you. Yeah. Okay. How are your brains feeling? Okay. All right, next one says to find f prime of x and f prime of 0, and then do you recognize this function? What is it? Okay, so first we have, this is our function, so let's go ahead and take our function and find f prime of x. So if this is f of x, if we want to find f prime of x, we're just going to take the derivative of all of these terms. So what's the derivative of 1? 0. Okay. What's the derivative of x? 1. So x, 0 plus 1 plus. What's the derivative of x squared over 2 factorial? So we've got, that's too hard for my brain. Okay, I'm going to drop the 2 down. 2x to the first over 2 factorial. Is it okay if I show my work like that? Okay, and then the 2's do cancel, so you're right, it is x. I just needed to see more work. That was too much for me. Okay, and then the derivative of the next one would be 3x squared over 3 factorial, and 3 here would cancel with the 3 on the bottom and would leave you with 2 factorial. Okay, plus dot dot dot. Plus, and then what's the derivative of x to the n over n factorial? Okay, so if we were to simplify this, we would get 0 plus 1 plus x squared over 2 factorial plus dot dot dot. The n would cancel out with the n, and what would it leave behind? N minus 1 factorial. Is everyone okay with that? Okay. I would cancel with n and leave n minus 1 factorial behind. Okay. All right, so, and then f prime of 0 is what? Is 1. F prime of 0 is 1. Or I guess I pointed the wrong one, hold on. Not that one. F prime of 0 is that one. So the first derivative evaluated at 0 is the coefficient of the term to the first degree. That's how you find it. The coefficient of the term to the first degree evaluated at 0 is, the first the first derivative evaluated at 0, the result of that gives you the coefficient of the term to the first degree. Okay, the first derivative evaluated at c equals the number gives you the coefficient of the term to the first degree. So if you wanted f double prime of 0, that would give you the coefficient of the second one, not divided by the 2 factorial, but it'd give you the second one. F triple prime of 0 would give you the coefficient of the third one, not divided by 3 factorial. Remember how all the numbers go? If you had f of 0, that would give you the term that did not have an x on it. So f prime of 2, or f prime of 0, it gave us this. This ended up being the coefficient for x to the 1. That's all I was saying, is that since it was the first derivative, it goes with the x to the 1. Does that make sense? That's all I was saying. It was just very hard for me to phrase that sentence without my brain as a first period teacher. It's not very warmed up right now. Whew. Okay. Do I need to rephrase, or did we catch it that time? We got it that time? Kind of. So if it's the first derivative, it's the first degree coefficient. If it's the second derivative, it's the second degree coefficient. That's how we match them up.
But if you plug in 0, it would just be 1 because that would cancel. Like, that part doesn't make sense, like, saying, like, you plug in the number and it goes. Then what if your coefficient isn't 1 for that? And it'd be whatever the coefficient is.
Well, no, you do have to think about what the factorials would have been. You have to keep in mind the factorials. So in this case, it was nice because it was 1. So it was the degree of 1. Yeah, keeping in mind the factorials. Okay. Do you recognize this function? Yeah, it's e to the x. So what you'll notice is interesting is that f of x was e to the x. And then what was f prime of x? E to the x. So we know that when we're not dealing with Taylor polynomials or Maclaurin polynomials, we know that if we just have the function e to the x, its derivative is e to the x. And what we just learned is that if you take the Taylor or Maclaurin polynomial, the derivative rules that we had learned before this unit still hold true. That the derivative of e to the x is e to the x. The derivative of the Taylor polynomial for e to the x is the Taylor polynomial for e to the x. That is true also. Let that sink in for a second. Nobody had a mind-blown moment? It's cool, right? Derivative of e to the x is still e to the x even when you have this whole funky... Like, I believe it when it's as simple as, like, oh, it's one term, e to the x is e to the x, fine. But you guys, we had this whole string of things and it's still the exact same. Isn't that wild? Nobody? Okay, let's move on. All right, example 5. You guys. So hard to impress. All right, example 5 says, f of x is this blurby thing, and capital F of x is the integral of this, and f of 0 equals 1 to find f of x. So what are they asking us to do? They're saying we have e to the x, and they want us to find what? The antiderivative. Okay, what's the antiderivative of e to the x? It's e to the x. Okay, so what we're doing right now is we are showing that with Taylor polynomials, that the derivative and the antiderivative are going to be what you expect them to be, okay? All right, so we're going to go ahead and take the antiderivative of e to the x. 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus so there's our integral of e to the x. So what is the antiderivative of 1? Okay, so that's just x. What is the antiderivative of x? Yeah, x to the 2 divided by 2, right? Would you guys rather have me write it as a fraction or write it as 1/2 x squared? 1/2 x squared? Okay. Okay. What's the antiderivative of the next term? Yeah, x to the third, and then divided by 2 factorial, and then we would also have the 3 on the bottom. Are you guys comfortable with how I wrote that? One six is the same. And then dot dot dot. What would we do over here? You have the n factorial already, and then what would you do with the n plus 1? Yeah, you'd also be dividing by that. Okay. Okay, and then what do we have on the very end? What do we always put when we integrate? Plus c. Okay. So I'm going to go ahead and clean this up a little bit and write it so that it looks like a Taylor polynomial. Okay? So I'm just going to say that this is capital F of x. This is what we have. Capital F of x equals x plus, this you can rewrite as x squared over 2 factorial because 2 factorial is 2. So x plus x squared over 2 factorial. X to the third over 3 times 2 factorial is, or if you had written it as 6, 6 is 3 factorial. 3 times 2 factorial is 3 factorial. So what we have here is 3 x to the third over 3 factorial. And then we have x to the n plus 1 over n plus 1 times n factorial is n plus 1 factorial. Okay, so now it says take this and plug 0 in for x and plug 1 in for y. Are we comfortable with that? Okay. So f of 0 equals 1. So I'm going to plug 0 in, 0 in, 0 in, 0 in for all of these. So what happens when I plug 0 in for all of these? Yeah, 0 plus 0 plus 0 plus 0 plus c equals 1. And so what does my c end up equaling? Okay, so c equals 1. Okay. And so now I can say that this means that my antiderivative is, I'm going to take my constant and move it to the front because in these polynomials, that's where the constant is it's right in the front. So I'm going to say 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the n plus 1 over n plus 1 factorial plus dot dot dot. So what do you notice? It is e to the x. So notice they're the same, but they're all off by the degree that you would expect. So the derivative has dropped by 1 degree, the way that we would expect, and the antiderivative has increased by 1 degree, the way that we would expect. But overall, it still represents e to the x. So you can still see the derivative and the antiderivative in the nth term, but the pattern still represents e to the x. Okay? So you can kind of see the way that antiderivatives are reflected in the nth term. You can see that they do increase the antiderivative. You can see that the degree would change, and you can see that the degree would change in the derivative. You can see that the degree drops by 1 in the derivative, but you can see that derivative rules hold true. That e to the x is still e to the x, that derivative is still the case, that they're equivalent functions. The nth term, so the nth term is still going to give you the same thing. It's still you're still going to get all the exact same terms. But you can see that your derivative rules are working the way that they always work. That your derivative, you can see from your original function, that if you have your original function, you can see that your derivative rule does what it always does, that it drops by 1. And you can see that your antiderivative does what it always does, it adds 1. Does that make sense? But overall, your e to the x is still e to the x. The antiderivative is still e to the x. The derivative is still e to the x. So you can see that everything that we've learned before does what it has always done. All right, so next, example 6 says, give the Maclaurin series for x, then take its derivative to find a Maclaurin series for cos. Include the general term. So let's go ahead and look at the Maclaurin series for sine. So what is sine? You can look at the whiteboard if you forgot. Anybody? Oh, we're all just writing it down. Nobody's saying it all. Okay, so it's x minus x to the third over 3 plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot 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 plus negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial plus dot dot dot. Okay. Yeah.
I don't know. Okay. The negative 1 to n.
Mm-hmm.
Even if you plug in like, oh, I get it now. Never mind. I thought I was gonna figure it out.
Okay, so we're going to do d dx of sine x. So what's the derivative of x? 1. Okay. How do we find the derivative of x to the third over 3 factorial? Okay. And then x to the fifth over 5 factorial would be 5x to the fourth over 5 factorial minus 7x to the 6th over 6 factorial. Oh, over 7 factorial. Thank you. And then for the nth term, we're going to take 2n plus 1 times negative 1 to the n x. And then if we have 2n plus 1, we moved it to the front, and then we multiply. What's the new exponent? 2n, because we subtracted 1 from the exponent. Over 2n plus 1 factorial. Okay. So now we just have to clean all of this up. What is the derivative of sine? Cos. Okay, it's cos. So we got 1. So here we're going to cancel a 3 with a 3, which leaves us with a 2 factorial behind. So we have x squared over 2 factorial. Cancel a 5 with a 5, which leaves a 4 factorial behind. Cancel a 7 with a 7 factorial, which leaves a, or with a 7, which leaves a 6 factorial behind. And then here, the 2n plus 1 is going to cancel with the 2n plus 1, which is going to leave a 2n factorial behind. Okay, is that not wild? Cool? Not cool? I think that's really wild, how it all works out. Yeah, I think it's because math just works. Math is math. Math is math is math. All right, so the important thing to remember is that as you do these different special series, you can multiply or divide series by a constant or a variable. You can substitute series in for x. We did that. We did like e of x squared, we did e of 3x, we did stuff like that where you could like substitute things in for x. You can multiply or divide the series by a constant or a variable. So we did like x cos x, we did like 4 e to the x, we did stuff like that. You can add or subtract two series or a term to a series. So you could do like cos x plus sine x and like add the two together. It would not be fun, but you could do it where you just like added all the terms. It would be obnoxious. Now we learned that you can differentiate or integrate a series by taking all the terms and differentiating all the terms and integrating all the terms. And then last, you can recognize a series as a sum of a geometric power series, which we will get to later. We're not doing that today. So now when you do all these things, the radius of convergence may change. So that's something to keep in mind, is that the stuff that we've learned holds true. So the derivative of cos is still going to be negative sine. The derivative of sine is still going to be cos. The antiderivative of e to the x is still e to the x. All that stuff is still true, but the radius of convergence of the series, if you've already found it, might change, okay? So just keep that in mind. Okay, go ahead and turn the page. Okay, this page says find the interval of convergence for f prime, and the integral of f for f of x equals x plus x squared over 2 plus x to the third over 3 plus x to the n over n. So first, we're going to look at just f. So this means that we're looking from n equals 1 to infinity of x to the n over n. This is what we have. Let me go ahead and zoom in. All right, what is the center? 0. Okay, and now we need to go ahead and find the radius of convergence, and how do we do that? Okay. So we're going to say the limit as n goes to infinity of and I don't know if I've mentioned this in a video yet, I talked to one of the AP trainers that I had, and she said if you want to go straight to the point where you do keep it, change it, flip it, as long as you do that correctly, it's fine. So you can skip this step and go straight to the next part, and as long as you don't make a mistake, you're good. They'll count it as you showing your work. Okay, and so what do we get here? Okay, so I get x, and so what's my conclusion about the convergence?
Oh, you evaluated the limit already.
Oh, yeah. Here, I can show my work better. Is that better? Okay. Well, the ends are the same degree. So, what are the conclusions we can get with the ratio test that would be okay? It doesn't have to do with 0, it has to do with 1. 1 is inconclusive. Greater than 1 is diverges. So less than 1 is when it converges. So if x is less than 1, then this is going to converge. So if the center is 1, then we're going to say if the radius is less than 1, we're going to have a radius of 1, basically. So we're looking at from 0, we can go 1 to the left, we can go 1 to the right. So right now we're saying somewhere if our number is between -1 and +1, it looks like we'll be okay. So now we just have to look at, can I include -1 and can I include +1? Or should I not include those numbers and only include the fractions in between? Well, that's what we got to prove. So we're going to say our radius is 1 because of this, because we got a 1 here. Radius is 1.
Would you say, like, because of the ratio test that you just know the rules that you can't with this one?
No, you might be able to have 1. So we're gonna check it. So I don't know. I'm gonna put -1 to 1, and I just don't know if I can include those or not. So we're gonna have to check. We'll look at -1 to the n over n. So there's the negative version. And then we'll look at n equals 1 to infinity of 1 to the n over n. There's the positive. So here we are checking -1. Here we are checking +1. Okay. So when we check -1, what test is this? Say it again. It's not nth term test. It's not geometric. It's alternating series because it's -1 to the n, so it's alternating. So we're doing the alternating series test. And what's the first part we do for the alternating series test? So limit as n goes to infinity of 1 over n. Make sure it equals 0. And does it equal 0? Yes. Okay, what's the second part we do? Okay, make sure that's true. Is that true? Yes. Okay, so that means that -1 is good. Based on the alternating series test, we're going to include -1. Okay? Now, +1 is 1 to the n. 1 to the n is always 1. So this is basically 1 over n, which is a harmonic p-series. What do we know about harmonic p-series? Okay, so this was converging, this was diverging. So that's your interval right there.
Where would we plug these numbers back into?
This.
That. Correct.
Uh-huh.
Oh, and that's why.
Uh-huh. Okay, how's your brain feeling? Okay, so that is check. We just did the function itself. Next, we're going to do the derivative of the function. Yeah, you could see I was writing really small. Now you know why I was writing really small. You're like, Ms. Rice, why are you writing little? You don't normally write that little. Okay. Whew. Okay, next one. F prime of x. So the derivative of each of these. So f prime of x, the derivative of x is 1. The derivative of x squared over 2, 2x to the 1 over 2, 2's cancel, okay, it's just x. The derivative of x to the 3rd over 3 is 3x squared over 3 is just x squared. Are we comfortable with that? Okay. Plus, and then x to the n would be n, x to the n minus 1 over n. Whew. Okay, our brain's okay? Okay. So this is going to be n equals, I think it's 1, because we have to make sure we get a 1 first. Yeah, 1 to infinity, x to the n minus 1. Why couldn't it be what?
N equals 0, x to the n.
You need to get a 1. Oh. Well, this is the nth term, so you're going to be using this as part of your formula anyway. If that's your nth term, that's going to be in your series. Yeah, in your notation. Okay. So, what's the center? Center 0. Are we all cool with how we find the center? Yes? It's just because we have an x. We don't have an x minus 2. If we had x minus 2, the center would be 2. So because we have an x, the center is 0. Okay. We do not know the radius. How do we find the radius? Ratio test. Okay. So limit as n goes to infinity of n plus 1 minus 1 over x to the n minus 1. Are we comfortable with that? Yes? Comfortable? Say it again. Move the x. It's to a negative exponent, so I moved it to the top. Okay. And then when we get to the end, it's the same that we had before. It would need to be less than 1. Our interval of convergence we're going to talk about is going to be 1. So we just have to see, we know for sure if it's less than 1 that we're good, those fractions are good. We just have to see what happens at 1 exactly. So that radius is 1. Radius is 1. Our interval from 0, we're going to go left 1, we're going to go right 1, so we're talking about negative 1 to 1 again. We're just not sure if we should include those or not. Okay. So we're going to check negative 1, we're going to check positive 1. So I'm going to take negative 1, plug it in. Take positive 1, plug it in. And then what type of test could I do? Do nth term test. There's another test you could do. Do alternating series test for this one. What test could you also do for both of them? Geometric. Geometric would work for both of them because it's something to the nth power. So if you did geometric for both of them, or nth term test for both of them, what would your conclusion be? Diverges. Yeah, so here with geometric, your r is -1. Here with geometric, your r is +1. So that's diverges conclusion for both of them. Nth term test with this one, you'd have +1, -1, +1, -1, +1, -1, so ±1 oscillating as it goes to infinity. Here, +1 as you go to infinity. Yep, +1. So either way, whichever test you end up doing, you're going to get diverges. It doesn't really matter. So whichever test you want to state for that one is fine. So I'm going to do r equals -1, r equals +1, geometric, diverging. Which means since both of them are diverging, we're going to do parentheses on both. We are not going to include either end. So as long as you use like -8/9, +7/9, +5/6, +3/4, +1/2, -2/5, all those are good. You just can't use -1, +1. It is a geometric. So any fraction where the denominator is bigger between -1 and +1, any fraction would be fine, would work just fine. But -1, +1 are not going to work. Yeah. Which totally makes sense when you look at it. You're like, yeah, absolutely, that's totally geometric. Yeah. Okay, how are your brains feeling about like understanding this? Is it making sense? Okay, so let's do the third one. I think we're getting to the point where it's starting to feel redundant, which isn't necessarily a bad thing. So now we can see the third one and see how the third one works, and then I think we'll be good. We won't need to look at it again. So we're taking x squared over 2, x to the third over 3, and now we're doing the integral of that. So the integral of f of x, the integral of x is 1/2, oh, there should be a dx here. 1/2 x squared, okay. The integral of x squared over 2 is x to the third over 2 times 3. So 1/6 x to the third. Are we cool with that? The integral of x to the third over 3, 1/12 x to the 4. And then x to the n plus 1 over n plus 1 times n. Are we okay with that? So this would be we don't really, because they didn't give us a starting term. Our starting term is this one. It's a good question. I think let's leave it out for this one just because I don't know that ultimately it makes a difference for the center and the radius and that sort of thing, because you don't necessarily need the very first term. I think the plus C would be like your very first term, and I don't think that it matters so much for this, but that's something I could look into. That was a good question. But this would be enough to get you to the rest of that part for what you need. Okay. Any other questions? Can you guys see how it would work? Okay. All right, so what's the center for this one? 0. Okay. And then what should we do to find the radius? How do we find the radius? Ratio test. Okay, so we're going to do the limit as n goes to infinity. Mm-hmm. Mm-hmm. I didn't have nx squared because the one of the x's cancels on top and bottom. You just end up with 1 on the top. Because you have x n plus 2 on top and then x n plus 1 on bottom. So 1 cancels. Yeah. So we ended up getting that the radius was 1. So the radius of convergence can change, but the radius itself has stayed the same every time. Have you guys noticed that? The radius is 1 every time, although whether or not the 1 is included has changed. So we're always getting the radius is 1, the radius is 1, the radius is 1. It's just whether or not we should include that 1. That is what has been changing. Does that make sense? Okay. So interval is going to be negative 1 to 1. And we got to see what should we do about that. So we've got check negative 1, check positive 1. Mm-hmm. Plug it in for x. So when you check -1 and you do the alternating series test, it converges. And then when you check +1, 1 to the n plus 1 is just 1. So it's like having 1 over n plus 1 times n. And can you guys tell what test that is? It's not a p-series, but you have the right idea. You're comparing it with a p-series. So you're comparing, and what p-series are you comparing to? With 1 over n squared. And that's a direct comparison, and 1 over n squared does what? It converges. So it converges by the direct comparison test. So all three of these, we had the original function, or I'll leave it up on the screen. We had the original function, we had the derivative, we had the integral, so all three of them were related. They had the same center, they had the same radius of convergence, but they all had different intervals of convergence with whether or not they included the endpoints or not. So they were related, but not completely related. Okay. I'm going to leave off example 8 because I think we could do it. Yeah. I wanted to show you guys how when you do this, just so you guys could really see, it's one thing for me to say that it works, it's another thing for you to see it firsthand. So I wanted you guys to see, yes, the center would be the same every time, yes, the radius would be the same every time, but oh, the interval could be different, and this is how it could be different, just so you guys could see, yes, it truly does hold true, because that's something that you can use in an FRQ where you can say, look, I know that the radius of convergence was this for the original function and I just found the derivative, so I'm not going to do the ratio test again because I know the radius of convergence is 1. Or I know it's 2. So I don't have to do it again. I know it's going to be the same. I'm just going to check the endpoints to see what the interval is. I'm just going to check to see if the endpoints are going to mean that they're included or not. I don't have to check it again. Does that make sense? And this way, since we spent a chunk of time on it so you guys could see that it worked every time, it's more memorable than if I just said it in 30 seconds and we moved on. Yeah. Okay, so for our assignment today, it's going to be kind of like on Friday, we're not going to do the whole thing because remember, Wednesday is going to be a work day for us where we don't learn anything new, we just practice. Okay? So let me get this handed out and then I'll look up the assignment and see which problems we're doing.